when you think of these multipliers, you have to think of them differently in case of continuous mechanics, a continuous time than discrete time. So if you're, so how to plot them? Eigenvalues. If you have discrete time, n equals 1, 2, 3, if I'm just going forward in time, then the only object that I have is this matrix. I don't have that other object, the matrix of velocity gradients. That's intrinsic to continuous flow. I just have J. So when you want to tell me about some property of your trajectory, what you should do is you should write in the complex eigenvalue plane, you should look at the real part. If eigenvalue is real, then it's on this axis. But you also, with kind of 50-50 probability, can get complex pairs, because there's no reason why not to get them unless there's some, unless Riemann hypothesis at work, or you're looking at quantum mechanics or some magical thing happens. But usually both of them happen. And now the most important thing about these multipliers plotted in a complex plane is that there is a unit circle, which doesn't look like a circle. Okay, I'll stand there. That's a unit circle. So this is 1, minus 1, minus I. And if something is on a unit circle, it means that that particular eigenvalue has magnitude 1, and that will be called marginal. Now, marginal eigenvalues, for generic matrix, you don't expect anything to be on any line, because that's a small set in a plane. So you don't expect to see marginal eigenvalues, but the moment you have some symmetry, this can happen. So they're extremely important, and they typically have to do with symmetries, as we all do. And they're very painful, it turns out, because you have to, testing where something exponentially unstable or stable is very easy, but testing where something is marginal is very painful, because you can spend a long time and not be sure it's marginal, unless there is a reason why that should happen. So now if I get some eigenvalue outside, so let's see, my lambda 1 is, for example, real sitting here, that means that when I look at the dynamics here along the first axis, I'll find out that in that direction, as this moves around, in that direction, I will actually be stretching, and I'll be doing this multiplicatively by this multiplier. So that means that distances expand along those directions, having to do with this eigenvalues. And there could be a complex pairs, but the main thing is we care about the magnitude that to explain the. Or they could be inside, so they could be here, or maybe here, or maybe there. So all these guys are contracting. So when we say something is unstable, we will usually mean it in a linear fashion, and we'll say that this particular trajectory is unstable, meaning that it has some, in linear approximation, it has some eigendirections in which I go away at exponential rate. Or there could be other direction in which I keep getting pushed in because the multiplier, its magnitude is smaller than 1. and that will be called stable. The main thing that we'll care about neighborhoods is to classify everybody in a neighborhood into directions which are unstable, where things blow up. That's what we really worry about, because if you want to control, let's say, heart or a magnetic levitation train, then we want it to be stable. So we don't want it to just go exponentially fast off the tracks. So those guys we have to control, so we really care about, and that's very important here. Then there'll be these guys who are marginal. You know, someplace there will be 1 in this set. And marginal ones will give us lots of pain, so we'll spend a number of lectures studying what symmetries do to dynamics, and that has all to do with marginality. And the contracting ones we don't really care about, because they take care of themselves. So if I do perturbation in contracting direction, it'll just heal itself. And this is actually the reason that this subject, which was originally developed as a theory of ordinary differential equations, also works for partial differential equations. You know, partial differential equations are morally an infinite set of ordinary differential equations. So if you have something, you know, some field you write in terms of Fourier modes, that's a set of ordinary differential equations. And if you can show that your system has 3 unstable directions and 17 million stable directions, 17 million stable directions will take care of themselves. We will only have to obsess about unstable ones. So that's why this theory can work for systems which are very large dimensional. The theory will develop. So it's, you know, implicit in this notion of stability.